Hey everyone, and welcome. Every single second, your computer is doing billions of things that honestly, they feel like pure magic. But you know what? It's not magic. It's actually a stunningly fast and incredibly precise process. Today, we're going to pull back that curtain and really see what's happening inside the box.
It all starts with something so simple. Let's say you're coding. You type out a basic line of code, something like z equals x plus y. To us, that's just a simple instruction. But for the computer, that one line kicks off this just incredible chain of events. So how does this hunk of metal and silicon actually figure this out?
Well, a great way to think about it is like this. Your command is like a message that has to be delivered, processed, and then acted on inside this bustling, microscopic city. And this city, it has its own districts, its own workers, its own communication systems, and they're all working together at speeds that are just almost impossible to imagine. So come on, let's take a tour. All right, so before we can follow our little command on its journey, we really need to meet the main characters in this story, the key components inside this city that make everything happen.
First up, we've got the star of the show, the CPU, the Central Processing Unit. This is the brain of the whole operation. Every single calculation, every decision, every single instruction you give your computer is ultimately handled right here. It's the master architect of this whole digital city we're talking about. But a brain can't do much without information to work with, right? And that's where memory, or RAM, comes in. Think of it like the CPU's personal workbench. It holds all the tools and materials, the programs and the data that the CPU needs to get to super fast. The only catch is it's volatile, which just means it gets wiped clean when you turn the power off. But for anything you're actively doing, it's absolutely essential. Okay, and finally, how does this whole internal city even talk to us in the outside world? It does it through its senses, the input and output, or I/O devices. We're talking about your keyboard, your mouse, your screen. These are the bridges that let the computer get commands from you and send the results right back.
Okay, so we've met the main players. Now let's get back to our command. Our little instruction, z equals x plus y, is written in a language that you and I can understand. The thing is, the CPU, well, it needs a translator.
And this is where things get really fundamental. The CPU, it doesn't speak Python or C++. It speaks one and only one language, binary, a series of ones and zeros. That's it. So the most important step is that our human-friendly code has to be translated into the only language the machine actually gets.
And this table, it shows that translation process perfectly. There's a special program, it's called a compiler, and it basically acts as an interpreter. It takes what we wrote, something we can read, and turns it into this long string of binary machine code. This is the version of our command that the CPU can finally work with.
All right, so our command is translated. It's now in binary, just sitting there in memory, waiting. And this is where the CPU starts its most important job, a fundamental process that repeats over and over again, called the instruction cycle.
This cycle is kind of like a super simple but really powerful three-step dance. First, the CPU fetches the instruction from memory. It grabs it. Then, a part of the CPU called the control unit, think of it like a traffic cop, decodes that binary instruction to figure out what to do. And finally, the arithmetic logic unit, or ALU, gets the green light and executes the command. It does the actual math.
Fetch, decode, execute, right? Sounds simple. But here's the part that'll just blow your mind. This little dance, it happens billions of times, every single second. And if it's constantly going to memory, that should be a huge bottleneck. So how in the world does it keep up? How does it get so fast?
Well, the secret is a couple of really clever tricks for managing how it gets data. The two biggest secrets to how fast modern computers are: caching and this awesome idea called the principle of locality.
See, the big problem is that main memory, it's just kind of slow. Going all the way out there to grab data takes precious time. So what engineers did was add a tiny, but unbelievably fast piece of memory called a cache right next to the CPU. And this analogy is perfect. You're not going to run to a giant library every single time you need a tiny piece of information, right? No, you keep the books you're using right there on your desk.
But okay, how does the computer know which books to keep on its desk? It all comes down to this brilliant observation. the principle of locality. It's just the idea that programs tend to use data that's all clustered together. So if the CPU needs one piece of data, there's a really high chance it's going to need its neighbors, or that same piece of data again, very, very soon. So the cache smartly preloads all that nearby data, saving a trip to that slow main memory library.
Okay, so let's recap. We have a CPU doing its fetch, decode, execute dance, using a super fast cache to speed things up. What's just incredible is that this whole elegant system, it's not new, not at all. It's based on a blueprint that's been around for decades.
I mean, the road to the computers we have today was paved with some huge breakthroughs. We went from room-sized machines like ENIAC to the first computers you could actually buy. But a real game changer came in 1949 with a machine called EDSAC. It was the very first computer that could store its own program instructions in its own memory. And that idea, it changed absolutely everything.
And that revolutionary idea, that became the core of what we now call the von Neumann architecture. It's the simple but totally profound idea that the instructions, the program, and the data for those instructions, they all live together in the same shared memory space. And the whole fetch, decode, execute cycle we've been talking about, that's the engine that makes this architecture run.
And here is the real kicker. That basic design, thought up way back in the 1940s, is still the blueprint for pretty much every single computing device you use today. Your phone in your pocket, your laptop, even the biggest supercomputers on the planet, they're all direct descendants of this one elegant, incredibly durable idea.
So there you have it. The secret life of a command is really a story about translation, a simple three-step dance, and a super clever trick for speed. All of it built on a design that's more than 75 years old. It's just a testament to brilliant engineering. But that leaves us with